Good morning, good afternoon, good evening, good wherever you are, ladies and gentlemen. And thank you for coming along to our webcast this afternoon. The IP-based object drives now have a management standard. So before we go any further, just a little bit about the interface that you have in front of you. You'll find that you're able to expand the size of the slides should you wish to by hitting the little expander on the bottom right-hand corner. If you hover your mouse over the picture, you'll see there's a little expander. You can expand out to full screen should you wish to do that. There are two other tabs that I want to bring your attention to. The first is a question. If you want to ask any questions of our presenters, please do so, and we'll try and take as many of them as we can during the presentation. And secondly, rate this presentation. As you're leaving the presentation, I'd be really appreciative if you could actually mark us on a scale of 1, goodness, I should have been off playing golf, to 5, excellent, more of this. This is the kind of stuff that we need to hear about. I'd be very appreciative if you do that at the back end. I'm also going to make a slight apology about the quality of the sound this end. You may not hear it, but some of you may. There's a slight echo. However, I'm sure we'll deal with it as we go along. So, without further ado, I'm going to introduce the speakers today. We're joined by Enrico Signoriti. Good morning, or is it good afternoon for you, Enrico?
Good morning, everyone.
Good morning.
Whatever.
Oh, good afternoon, whatever you are. We're not in the same room, as you can probably tell here. And by David Slick. Hello, David.
Hello.
Eric Rydell. Hi, Eric.
Hello.
And there he is. Good. He's come off mute. And myself, I'm the co-chair of the SNIA CSI here, and I'll be the host for this presentation. I'll introduce our speakers as we get to each of them in turn. So, just very quickly, SNIA at a glance. What is SNIA about? SNIA is an organization that focuses, as its name would suggest, is a Storage Networking Industry Association. It focuses in on storage and network storage in particular. It's got 160 unique member companies that contribute to its work. It's got 3,500 active contributing members, and it's a worldwide organization extending out to the Japans, to Asia, to Europe, and obviously inside the US. You can learn more at snia.org/technical. In fact, snia.org is the main landing site for SNIA itself. And I welcome you to take a look around our site. At the end of this presentation, we'll be also putting this presentation up on the website for you to be able to see for your own use. I'll point out the address of that when we get to the end of the presentation. And secondly, we'll also be writing a brief blog to cover some of the questions that may be asked during this session. So that's about SNIA. Very quickly, a legal piece. This basically says, if you use this presentation, remember it's our copyright and we'd like you to attribute any use of it to SNIA. And secondly, if anything you do as a result of this presentation causes whatever you're doing it with to fall into two parts, both parts are yours. There's no warranty with this at all. That was notwithstanding, we are in the business of providing you with quality information. So be assured we're going to do our very best today. So, without further ado, I'm going to introduce very quickly our speakers. First today, we're going to be getting an object drive overview from David Slick. David works for NetApp, and he's a technical director there in managing capacity storage. He's been involved in object storage for over 15 years. He's also the co-chair of the SNIA Cloud Storage Technical Working Group, which developed the CDMI standard, which is a cloud data management interface standard. And also a member of the Object Drive Technical Working Group, hence the background today. We'll also be joined by Enrico Signoriti. I'm sure I'm getting Enrico's name, or I hope I'm getting Enrico's name right. Enrico works for OpenIO, and he develops roadmaps from planning stage to development to ensure market fit, represents his company at industry events, and actively participates in the company's sales efforts, etc., etc. And I know Enrico. I've met Enrico several times, mainly in San Francisco Airport, and it's nice being on the presentation with him today. And lastly, we're also joined by Eric Rydell. Eric is Senior Director of Technology and Architecture at the Unstructured Storage Team, which sounds pretty suitable for this kind of presentation, at Dell EMC. His group designs, builds, and helps deploy scale-out distributed cloud and big data storage. And he's going to talk to us today about some experiments and experiences in building object storage and using object drives. So, without further ado, I'm going to let David Slick take us through the object drive overview. David, over to you.
Certainly. Well, thank you very much for attending the webcast, and we're going to talk a little bit about what do we mean by an IP-based drive, what do we mean by management for these devices. So, the big change is around how you talk to these drives. As you're probably all aware, we've had many, many years where the mechanisms by which we communicate with our storage devices is primarily SCSI-based. Whether this is over fiber channel iSCSI, direct attached via SATA, SAN, SAS, fabrics, etc. It's been a familiar protocol that has served us very well. But as we've seen, there's been a lot of transitions towards IP-based technologies, IP-based connectivity for many reasons. And as a result, we've done a lot of work to look at how drives can be connected via IP protocols, and in order to manage these, how these IP-based drives can be managed. So, as part of this work, there's a technical working group at SNIA specifically focusing in on how we manage these drives, and the address is here. We'd encourage, if this is an area of interest for you, please take a look at the website and join the technical working group. And we're always looking for more folks from the industry to come contribute to help make everything better for everybody. Okay, so why are things moving towards IP-connected storage devices? Well, the short answer is because they are. Because the market is already demanding the flexibility, the scale, the rapid development that comes with loosely coupled IP-connected devices. And this is just a logical next step, to take IP connectivity instead of just to the storage system all the way down to the individual drive. So why would you want to do this? The traditional model today is you have a storage shelf with some sort of controller, and it's connected via fabric to the individual drives, and then you've got 10 gig E or 40 gig E out the back, etc. Why take IP, why take Ethernet all the way down to the individual drive? Well, there's a couple of reasons. One of the first reasons is scaling incrementally. By having individual drives that talk on the fabric, you can just add drives individually rather than having to add them at the shelf level and then populate those drives. So that's one aspect. There's also simplicity. You don't have to have extra layers. You're not going through translation layers. You can have applications talking directly to the drives, and you can have intelligence embedded directly into the drives that you communicate with via application-specific protocols. So there's lots of flexibility as well. And we're starting to see this already adopted in both commercial and open source systems. For example, there's HDFS, Lustra, Ceph, Swift stacks that will be able to talk directly to these IP-connected drives, and with increasing adoption comes the need for management. So, who would buy these IP drives? Well, system vendors and integrators see advantages here. It lets them reduce their time to market, focus on features rather than just the plumbing of necessarily translating between storage protocols, etc. Hyperscalers are deploying these types of technologies extensively, focus specifically on how can we reduce every piece of complexity that isn't directly contributing to the functionality we're providing. And of course, enterprise IT is closely watching what's going on in the hyperscale environments to look at how they can adopt these technologies to help their business. So we're seeing more and more of these going into systems. You may even have some of these drives in your systems today, or maybe using these drives behind your cloud services and not even be aware of it. And we expect to be seeing many more over the coming years. So what does a traditional block storage device look like? Well, you have your underlying drive, whether it's spinning disk or some sort of non-volatile memory, flash, etc. And then you've got either an ATA SCSI or NVMe connection going over your SATA, SAS, or PCI interconnect. And these devices, they're locally addressable. They're on a local fabric. And the protocol itself is based on block I/O, and it assumes that there's a reliable transport. It assumes that there's long-lived local communication, i.e. that you have a controller talking to drives, and that topology is relatively fixed and static. When things change, that's usually as a result of a failure, a maintenance event, and all of the accesses to the drives is heavily coordinated. You don't have multiple systems talking to a drive at the same time. Typically, you have maybe failover that happens in a failure event, but other than that, there's one initiator talking to a number of targets, and that relationship is fixed. So how does that look when we move over to IP-based drives? Well, the bottom of the stack looks the same. You have your underlying storage resources. But at the top, this is where things are different. Instead of a fixed block-based protocol interface, you now have storage services that can be many things. These could be a key value store. These could be block level address access. The neat thing about this technique is that this can be programmable. This can be user definable. In some of these drives, you can load in your own code to provide processing and protocol processing directly beside the storage embedded in these drives. In other cases, they're running stacks, key value access, etc. And this is connected via Ethernet over IP protocols. So what does this mean? You've got a connection via Ethernet. It's potentially globally accessible. It's certainly accessible within the data center. It provides storage services directly to clients. And this has a lot of consequences. You're typically looking at higher level storage services. You are dealing with error-tolerant protocols such as TCP/IP, where you may have situations where that network isn't as reliable as that local fabric inside that storage shelf used to be. It's not a model of just one initiator talking to one target anymore. You have more along the lines of transitory global communication, where you have many, many, many clients that for a short period of time may establish a session to that IP-based drive or collection of IP-based drives to perform a transaction, and then it goes away. And another set of clients may then initiate the next transaction, etc. And you have a lot of concurrent access. So instead of everything being funneled through one controller, applications, clients just access the storage resources they need. And this results in a different model because you're having to deal with much more dynamic clients that are coming and going, etc. And this is where a lot of the complexity and performance and scale comes from, because instead of having to take all this client workload, concentrate it into one controller, and then fat it out to the drives, the clients can do that directly to the drives themselves. So, how is this managed? Well, the Object Drive Technical Working Group has produced a specification for how to manage these drives, and it's based on the Redfish management specification from the DMTF, that's the Distributed Management Task Force. So to give a quick overview of Redfish, in the case you haven't encountered it before, what Redfish is it's a RESTful HTTP-based API for discovery, management, configuration, firmware updates, logging, etc. of devices commonly found in the data center. The DMTF has standardized what you'd expect for a server or a basic network switch or your UPS, etc. Your standard resources. And in the Object Drive Technical Working Group, what we did is we took the standard, it's extensible, and we extended it to be applied to the specific scenarios you'd see for these object drives. And one of the nice things about this is it's a very small net incremental change to a standard that's being widely adopted and is very easy to develop and implement. And we gain all of the benefits that come from that larger standard. So, what sort of things would you use this for? What sort of management challenges do you have for object drives? Well, it's got to talk to the network. Unlike the traditional drive, which comes shipped in a fabric in a predefined situation that's all being tested and pre-configured and is a relatively self-contained environment, this is talking to the wild network. So you don't necessarily know beforehand what it's going to be plugged into, how it's going to be communicating, etc. So you need to make sure that this drive, from a management standpoint, can physically connect to the network, can configure itself, get an IP address, figure out how to talk to the DNS servers, how to get time services, etc. And how to figure out where it's physically located. This is a very important thing for drives, because if you have a drive failure, you want to be able to identify where that drive is located so someone can go out and do a maintenance operation on that drive. And you want to make sure you get that right, because if you tell someone to go and pull the wrong drive, you may make a problem, a small problem, into a larger problem. So this is an example of something that's very important for these object drives. So what else? So that's some of the things that drives have to do that they need management information for. As a manager, whether this is network management for operations or whether this is software, being able to automatically discover, what drives are available, how are they allocated, who are they assigned to, what's the administrative jurisdiction of these different devices, how do I find out where they're located, how do I find out if they're connected, how do I keep track of things as they change, because this is a lot more dynamic. Instead of shelves where a lot of the times the drives are hidden and abstracted, the applications and the managers are now directly seeing these drives as separate entities on the network, and these are all critical roles for the management protocol. So in addition, there's all your firmware challenges. You have to manage not only the firmware of the drive. These drives typically have CPUs, whether that's running specific software or whether that's allowing you to load in custom software or applications to run software. How do you configure all this? How do you configure the network? If your drive supports multiple applications, let's say you can load containers on it, etc., all the way down to how do you select an application and configure the application. So that's a degree of management visibility that's not traditionally exposed with drives. And very importantly, security. Because these drives are directly connected to your network, usually your internal network, but as with these sorts of technologies, if it can be plugged into the internet, it will be plugged into the internet. So security is very important. How do you ensure, from a management standpoint, when security updates are available, what drives need the update to be applied, how do you push those security updates to the device, how do you maintain operations during these updates? So that may require coordination with the applications running on top of it, or it may not, because a lot of these next generation applications are designed to assume that a certain number of drives are not working at any given time and that a drive can just go away for a little while without negatively affecting application functionality at the higher level. It's one of the transitions that we're seeing, especially in the hyperscalers. And being able to make sure that everything's up to date and everything's maintained. So that's another very important set of management functionality. And in terms of operational management, how do you know when things are failing? Monitoring, environmental health. Is this drive running really hot? Has this drive got bad, vibration characteristics? You want to monitor not just the environment, the hardware, the data health, the application running on those drives, and not just knowing when something's gone wrong, but when something's about to go wrong or starting to become suspect. You want to know often before things actually fail so you can try to prevent that failure from happening in the first place. And once again, if something has gone wrong, how do you replace it? How do you know where it is? How can you trigger a maintenance event where ultimately someone may have to go out and physically replace something? Although a lot of times these drives are just left to fail, and then you have bulk maintenance events periodically, say on a monthly basis, etc. So all of these things are the requirements for how you manage these. And the IP-Based Drive Management Standard goes through and says, okay, you've got this drive, you've got Redfish, here's how you apply Redfish to these drives to accomplish these goals, these requirements. And it takes you all the way from the physical form factor up through the electrical link layer, network, connection, all the way up to application hosting, and talks through the different permutations of drive types and how you'd manage them differently, etc. So how do you do your IP address assignment, discovery, etc. So we think it's a good document, and we'd encourage you to take a look at it if you're involved either creating these sorts of drives or consuming services provided by these drives or looking at writing services that can run on these drives. And as always in SNIA, we're better if we have more people involved, and that helps us write standards that are relevant to your needs, and we always encourage you to become involved if you are not already. So Redfish specifically uses, if these IP address drives, the account service, which deals with who can do management operations, sessions with respect to who's talking for management purposes, chassis, the concept that you can have collections of drives, manager, which is the core management object, computer system, which is dealing with the abstraction that you can run things on these drives, and they've got a CPU and firmware. The update service, which is dealing with firmware for both security and regular, and there's also a disk property which talks about your underlying storage. And one of the nice things about this is once implemented, if they are already using Redfish for management anywhere else, this just slides into the standard framework, so it should work with your existing management tools. And we also provide a series of mock-ups. What these are is examples of what sort of RESTful responses you might see from an IP-based drive. And these can be downloaded from the SNIA website at Object Drives. In addition, we have the Redfish schemas, and we show examples of just a single drive as well as a collection of drives. So that's another great place to go and look if you want to see what one of these look like. And with that, I will pass it on back to Alex.
Thank you, David. Quick questions for you. There's a couple of questions that we have. The first one was, and I suspect you answered the question indirectly, each drive has its own unique IP address, yes?
That is correct.
Okay, and I'm presuming that the specification we've been talking about as well, it's also been going under the name Swordfish, hasn't it?
Swordfish is slightly different. So Swordfish is another parallel group we're working on within SNIA, and what it's doing is it's looking at taking the broader storage management functionality that you typically see, for arrays, for storage virtualization, the sorts of things that you'd see with, for example, SNIS, and saying how can this storage management fit into the Redfish world. Now, as a result, that's very complementary, because let's say you want to have additional management functionality for these IP-based drives that isn't expressed through the very basic storage management capabilities of Redfish itself. Swordfish extensions allow us to express how to do things like, for example, rating, etc. So if you're interested in Redfish-based management, also take a look at Swordfish on the SNIA site to see how advanced storage management is in the process of being standardized.
And one last question for you at the moment. Would a drive with iSCSI protocol and an Ethernet interface be considered an IP drive?
Absolutely.
Yep. So you can actually have an Ethernet addressable iSCSI interface or stack.
Yeah, and whether the drive comes pre-configured with that, you just take the drive, plug it in, go through the management interface, and you have iSCSI LUNs, or whether that's a little application that can be downloaded onto the drive that gives it the personality of providing iSCSI-based storage. Both those will work through this management interface.
Okay, well, thank you very much, David. Keep those questions coming. Remember, you've got the question button at the left-hand corner that you can use to ask a question of our presenters. So, without further ado, I'm going to pass over to Enrico Signoretti, just to remind you that Enrico works with OpenIO and represents the company and its products at industry events. And Enrico is going to take us through some commercial offerings in this space. Enrico, over to you.
Okay, thank you very much. And so this is an example, for example, of our position in the market. There are several designs similar to that. And it's just an interposer. Commercially, we call it nanonode. There are microserver, micronodes. Each vendor has its own name, but actually all of them are based on ARM CPUs, usually two-core CPUs, not very powerful, in the range of 1.0, 1.8 gigahertz, and each of them with 1 or 2 gigabytes of RAM, a little amount of flash memory, some of it for the operating system, and a little bit more, like in the range of 32 to 64 gigabytes for storing metadata, for example, for object stores. And these devices usually have two 2.5 gigabit ports. Okay, they are really efficient from the power management point of view, and they support every type of SATA drive in the backend. If you noted that the device has a standard interface, in fact, it could be inserted in a standard JBOD, okay? And the JBOD is usually it usually has multiple power supplies and cooling units as its chassis management. But actually, instead of having two SAS expander in the backend, usually it has two switches, okay, that connect all the internal links and provide a few ports for external connectivity. In some cases, these devices have the ability to connect back to back. So at the end, you have only a few cables remaining for the uplink connectivity and external connectivity. But actually, they are really dense. In this case, 96 in 4 units, in 4 rack units. There are, as I said, several designs on the market already. Some of them are a little bit different because they don't use the interposer, but actually the concept is identical, and they start with 8 drives up to 30, 48, or 96, like in this case. The internal architecture, as I already explained, has these 2 switches in the backend. They connect all the nanonodes. So each single nanonode has a double connection for redundancy, and so the quantity of bandwidth available to each node is more than enough for an hard drive, okay, SATA drive, but also for smaller SSDs. The same software that usually is installed in Linux servers can be installed on this kind of systems. Okay. In the market, you can already find implementation of Ceph, Swift, and our SDS, for example. They are all available. I don't know about commercial implementation yet, but it doesn't mean that they don't exist already. So it's quite easy to find an object storage system starting to implement this kind of technology. Of course, by doing so, you provide a failure domain, which is the single drive, and it's really convenient for some customers. And for this, I can hand over to Eric.
Thank you, Enrico. Just a quick question for you. How much is that interposer adding to the cost of the drive? Is it significant, or is this a fairly cheap piece of technology that can turn a standard drive into an IP-based drive?
Actually, the cost of the enclosures is around 40, 50 euros, which means 52, 55 potentially dollars.
Okay.
So it's not very expensive. Okay, maybe with the quantities, it could be even cheaper.
Okay, so the goal is presumably we can start by using interposers, and the drive manufacturers presumably at some point get involved and start manufacturing drives with these electronics on board, I would imagine.
Yeah, actually, my expectation is that the hardware vendors, so the disk drive vendors, will start implementing this, and they will provide us with a full-fledged IP hard drive, okay, that can install a narrowed down version of Linux that we can use.
Okay. Okay, thank you very much, Enrico. That was most helpful. So we're now going to pass over to Eric. And as I said before, Eric is the Director of Technology and Architecture at the, I love that phrase, unstructured storage team. Wonderful thing, at Dell EMC. And Eric's going to take us through some of the experiments and experiences in building object systems and using object drives. Eric, over to you.
Thanks, Alex. So I'm going to take off from where David and Enrico brought you as far as standards and individual devices. I'm going to talk about a system level view of why we would want to use these object devices and kind of give the business and the technical rationale. So the primary reason that we're interested in IP connected drives is to achieve the level of scale that we need in our unstructured object storage systems. And so I've worked on two separate products in my time at EMC, and I've been working on object drives for most of my career in one form or another. But let me just take you through kind of the last 10 years or so of history in terms of unstructured storage or object storage at high density. Right? So when I first joined EMC, we were building an array, a 40U rack worth of disk drives and servers running object storage that was a whopping 240 terabytes within a single cabinet. So we had 16 servers, 16 enclosures, 240 drives total. So there was 30 drives per enclosure. So with 1 terabyte drives, that gave that entire rack that you see on the far left of the diagram was 240 terabytes in a 40U rack. Right? And then what I show in the table and along the bottom of the slide is how we've iterated that in the last 10 years. So we've moved through, in the capacity column, we've moved through 2 terabyte drives to 4, 6, 8. Today we're shipping 10 terabyte drives. That's obviously one of the big mentions of capacity increase, is individual drives having larger capacity. But the other dimension is where the challenge in terms of connectivity and manageability and serviceability, the types of things that David has already mentioned, really come in. And so you see that first system I talked about had 240 drives in the system, and the system that we're shipping today in 2017 has 784 drives. So we've more than tripled the number of individual drives that are in a rack. Right? And we've kept the number of nodes constant. I'll talk about that again in a moment. So we tripled the number of drives. We have 10 times the capacity on an individual drive. So that means we have more than a 30x improvement in the per rack density between 2008 and 2016, right? Which is pretty impressive in terms of scaling. right? Only the folks at Intel with their integrated circuits and chips and gates and so on are able to to come close to those kind of technology improvements. So that's the merit of the drive industry and the storage industry generally, right? So now, so keep this in mind: 780 drives in a 40U rack. And I've shown one of the set of choices that we made with enclosures on the previous slide, but there's a number of different ways that you can do enclosures. We started with this back-to-back front-loaded enclosure. You pull out the enclosure, you reach in for a second row of drives. There are drawer-based schemes. There's a scheme that we're using in our densest system of sleds. So they're individual collections of drives that are grouped together. You pull out an entire sled at a time. There are tray-based systems, which have been popularized by the Open Compute folks. And then various levels of modular, kind of front-loaded and rear-loaded drives. There's a number of different serviceability trade-offs. Do you want all the drives reachable from the front? Do you want to have to walk around the back to service some of the drives? How many drives are offline when you're doing a single drive replacement? And so there's a number of choices about mechanicals and electrical connectivity within these enclosures, but the goal is ultimately the same. Get the largest number of drives into a rack with the smallest overhead, right? And as I usually, when I talk about these systems with our suppliers, anything in my rack, in our racks that isn't a disk drive is overhead, right? We sell on dollars per gigabyte, and if it's not a disk drive, it's not contributing to the gigabytes, and it's making my dollars higher, right? And that's the raw material cost. In addition, any extra complexity or layer of software, layer of indirection, so on, is adding to the complexity of the system in terms of diagnosis, in terms of code that has to be maintained, in terms of, as David has already mentioned, different firmware that can go wrong, different interactions that can not quite adhere to standards no matter how long they've been discussed. Right? So there's a lot of different ways to do the mechanicals, but that end goal is largest number of drives in the same fixed physical space. And so on this next slide, I'm actually showing a history. This is originally from a presentation that I created in 2012 for a workshop at the Library of Congress, where what they had asked us was, in the next 2, 4, and 6 years, how would we design a system with 5 petabytes, 20 petabytes, and 50 petabytes worth of storage? And what the Library of Congress was expecting to hear at the time, back in 2012, was that obviously in order to build a 20 petabyte or a 50 petabyte system, you'd have to use high density tape technology. It couldn't possibly be done with disks. But we were, even at the time, proposing systems with disk drives, and you see some of that in the darker history in gray. But today, this is a matter of course, systems that are built as a matter of course. So we have customers that regularly buy 20 petabyte systems. Remember, I said on the previous slide, we have almost 8 petabytes in a single rack. So 20 petabytes of usable capacity can be done in a mere 4 racks, and 50 petabytes can be done in about 9 racks. And so that means that a 100 petabyte system would still be under 20 racks. So this is that same performance, the same capacity improvement in individual drives, and our ability to squeeze extra drives into the cabinets, both of which are allowing us to build very large scale systems. But as you see, in every system that's listed here, there are several thousand disk drives. And so our challenge is, how do we do the care and feeding of systems with thousands or tens of thousands, potentially, disk drives? And just to show you, what this looks like in reality, it's easy to put things into PowerPoints and into PowerPoint tables. This is a picture of one of our labs. And this is, what you're looking at here is a 6-rack system with a total of 23 petabytes, 48 compute nodes, and 2,800 disks. So we have 3,000 disks, approximately 50 servers. So you have 3,050 individual devices plus some switching that need to be managed. You need to worry about the firmware and the addressing and predictive health, and so on, all the things that that David Slick mentioned earlier, and you need to worry about it for 3,000 drives and for 50 nodes. So that was one dimension, the dimension of scale. The second dimension, where IP-connected drives become relevant for us, is in the flexibility that we need within these systems. And that's illustrated on this slide. So there's a lot going on this slide. People can look at the individual stack-ups on your own. The important thing is to watch the progression and compare the systems on the right with the systems on the left, and then the system in the middle. Right? So the systems on the right and the systems on the right are SAS-based systems. And what we're doing here is we're offering a modest-sized system at the far right, 320 terabytes, 4 nodes, 40 disks. And then we're progressively increasing the number of nodes and the number of disks as we go across. Then we increase the node-to-disk ratio significantly at our 1.9 petabyte system. Now we have 30 disks per node instead of 10 disks per node. And in the final incantation, we have 60 drives per node. And as one of the other, our densest enclosure today actually has 98, so almost 100 drives per node. So we need the same system, the same infrastructure, the same kind of physical set of components to handle an order of magnitude drive to node ratio. On the far right, you have 10 drives per node, and in the densest solution, we have 100 drives per node. And so the systems in the center with the orange at the bottom is an example of a system with Kinetic Ethernet drives. And in this case, we have created independence between the drives that are at the bottom of the rack and the nodes that are at the top of the rack. On the right-hand side, with a SAS-based solution, all of those drives, 60 drives or 100 drives, are directly attached to a single host. So every time I want to add a drive enclosure, I need to add a host. Every time I add a host, I want to add a drive enclosure. Right? In the system in the center with the orange, I can separately add nodes and separately add drives. So if a customer, as in the systems on the far right, if a customer wants, for example, just 12 drives and 4 nodes, they can do that with a single 12-disk Kinetic enclosure. Or if they wanted 4 nodes and 120 drives, they could do that with a set of 10 Kinetic enclosures. Similarly, we could go all the way up to having 700 drives and 4 nodes connected in the same system. So this is our second kind of CTQ in our design space. So we want both, on the one hand, the highest possible density, which I motivated in the previous set of slides, but I also need this flexibility to modify the ratio between compute and storage. In the best case, it would be done on the fly, but definitely we want it to be done incrementally as customers purchase more equipment. Right? They can purchase more compute if they need more compute. They can purchase more drives if they need more drives, but they're not tied in to a fixed ratio or anything on the mechanics and the electricity. So to give motivation, we've been trying to address this problem of this all-to-all connectivity for some time. So we started in 2012. We did some experiments, and experiment is probably an ungenerous word, so we came pretty close to shipping the solution, and ultimately decided for a couple of pragmatic reasons not to ship it, but we built a design and a whole series of racks and prototypes with this solution. We tried to use SAS switching. So as shown in the center of the diagram here are a pair of SAS switches, and the connectivity diagram, which is a bit hard to read eye chart, but you don't have to read the entire diagram. The important thing is that we took all of the nodes, which are at the top of the diagram, connected them into the switches. We took all the drive enclosures, connected them into the SAS switches, and then we were able to, under software control, reassign an entire enclosure between nodes. So the reason this is important is to be able to modify the ratio of drives to nodes, as I motivated on the previous slide, but also for fault tolerance purposes, right? So if I have one node that can see the drives, then if there's something wrong with the hardware or the software of that node, then those drives, 60 drives, 100 drives, are isolated from the rest of the system, right? If I do a dual, if I do, for example, active-active SAS-attached dual-ported drives, then I can have two nodes that are responsible. If one node is down, the second node is able to fail over. But when I discuss this with my software colleagues, they say, hey, Eric, one node, that's not enough. Two nodes is great, but it'd be better to have four. And then two nodes could fail, or even three nodes, I'd still have connectivity. And then once we start talking about four, they're like, Eric, if the system has 8 nodes or 12 nodes, it would really be best if it was just all-to-all connectivity. And that's what we were trying to accomplish with these SAS switches. But as I mentioned, back in 2012, there were some technological hurdles in being able to productize this, and so we didn't finalize the productization of that. So then in 2014, the Kinetic Technology came along. This is some overview presentation material from Seagate. So Kinetic is the Seagate term for the product name for their Ethernet connected technology, right? And this shows a number of the changes that are being made. We've only really been talking about the connectivity aspects of the change. That's what I'm going to continue to talk about here. David Slick did allude to, you can use key value APIs, you could use iSCSI, you can run different types of API codes, as Enrico mentioned, directly on the drive. So the ultimate decision of what you do logically in the protocol, what stack in the software, what set of APIs you use, is up to the integrator of the system. The key thing is that there is this unified transport layer. So you no longer end up with this separate SAS layer for communicating with drives and an Ethernet layer for communicating among nodes. You just treat nodes and drives as a flat space, right? And then just to be a little bit more concrete, the previous was a kind of overview architectural diagram. We started these experiments in 2014. There's an enclosure from New ISIS that is 60 drive, dual 10 gig switches on the back end. This is the same kind of chassis that Enrico described. So he described a 4U96. This was a 4U60 3 years ago. And then the first drive that we prototyped in that enclosure was a 4 terabyte, 2 by 1 gig disk drive from Seagate. And then in 2015, we had available 8 terabyte, 2 by 2.5 gig drive. And the change from 1 gig to 2.5 gig is actually relatively important in drive. So those who spend any amount of time with disk drives, you know that a disk drive bandwidth maxes out in the range of 150, 180, maybe 200 megabytes a second. If you were trying to run that, squeeze that all into a 1 gigabit Ethernet link, you'd be limited to 85, 90 megabytes worth of throughput. But if you do that 2.5 times, then you can cross the 200 megabytes per drive barrier, which is pretty much the highest bandwidth that those drives are ever going to produce. You also get a modest latency improvement if you're trying to do smaller requests. But the important part is really the bandwidth improvement. And so you don't have to go all the way to 10 gig. So it's one of the questions that Enrico was asked, you're not taking a huge cost burden by putting 10 gig PHYs and 10 gig networking onto these drives, but you are improving on the 1 gig that would be out there. And you're getting yourself back into the range of 3 gigabit and 6 gigabit where SAS would be as well. Right? So that was a significant innovation in that part of the space. And it's possible because the only parts that have to be 2.5 gig are those individual PHYs on the drive and the PHYs on the switch that is the controller backplane. Right? So there's nothing that has to change in the rest of the ecosystem. Everything upstream is 10 gig. And so that's actually shown here. So what I'm showing here is our second generation Kinetic prototype that we've had in the lab since the end of 2016. And we have the parts list is on the right-hand side. So I have 9 2U quad servers, so 36 nodes of servers. Each of those servers have 2 10 gig interfaces. Then we have a pair of 10 gig switches per rack. That's the green very much at the top. Those are interconnected together to form an aggregation layer. So it's basically dual 10 gig switches that do all the data path. And then we have 3 1 gig switches, one in each rack, and that provides the management connectivity. And the important thing for us is that this is a completely flat network. So this network has 36 servers, it has 18 drive enclosures in this case, and 714 individual disk drives. But those enclosures, drives, servers all have IP addresses. They're all managed on a single network. There's somewhat different concerns between managing them, but a lot of it is very similar. Managing the software or firmware that's on those devices, what's the difference between software and firmware? Not much these days. Depends on the functionality that you're looking to provide. But the kinds of things that David Slick was talking about, doing proactive error handling, addressing the drives, knowing where they are physically, directing a service person when they need to pull a node or when they need to pull a drive. All of those characteristics are common among drives, nodes, and enclosures. So it's very attractive for us from a complexity reduction perspective to be able to treat everything as an IP addressed, manageable, addressable component. Right? And in addition, we're able to satisfy the 2 goals that I laid out in my previous slides. We're able to get the most extreme scale that's possible. In this case, there's only 500 nodes, 500 drives that will fit in a rack. But there are enclosures such as the one Enrico showed, 4U96, that would allow us to get back to almost 800 drives in a rack. So this particular rack would only hold 1,500 drives, but we could imagine it being as high as 2,400 drives. And so we're able to achieve the density, plus we're able to achieve that flexibility. Right? I'm showing here 3 racks with 36 nodes, but we could imagine systems where there are 4 nodes or 8 nodes that service the entire complex of 1,500 or 2,000 drives. And then you have an incredibly good dollars per gigabyte. You've really squeezed everything out of all the excess cost out of the system, and you're able to still do very effective object management. Right? And if you need more compute, if you need more switch bandwidth, you add more compute, you add more switches. You're not tied to the tyranny of being connected to SAS and how much can fit in an enclosure and how many drives you can put onto a SAS bus and so on. And so then there's also data path connectivity that I've discussed. I'm not going to belabor this further here. And management path connectivity in order to provide a separation between management paths and data paths so that you can diagnose problems and better manage the system. So in summary, we leave a little bit of time for questions. We were able to create a software-defined storage solution, as Enrico motivated. We're able to do scale out with a very aggressive density in terms of petabytes per rack, a very aggressive cost, because we can simplify. We have less components, less cables, less code, less layers. I don't have to do translation from SAS to Ethernet and back again. I can just do everything directly on Ethernet. I can get common manageability between the BMC on a node and the management controller, the management software on the drive, etc. And I'm achieving flexibility, as I've already said. I'm able to adjust my compute and storage ratios. I can do it at purchase time, and over time, we'll be able to also do it dynamically. Right? So I could today be using a system where there are 10 drives per node, and tomorrow, those same nodes could be responsible for 100 or 200 drives. It's completely under software control, and the system can be reconfigured with addressing and assigning drives to nodes in the matter of minutes or even seconds compared to having to purchase additional gear. So we have achieved the flexibility and the scalability that we were looking for.
Thank you very much, Eric. So before we end the session today, I've just got a couple of questions for you, Eric. Let's see if we can just try to pick some of the questions here. All these solutions, how do they do data protection? RAID? Is it just, can we have drives that, perhaps there are a pair of drives in a single 3.5-inch enclosure? I mean, what kind of data protection can we provide at this level?
Yeah, so in our system, we do erasure coding across the drives. So we place fragments of data in an erasure coded group, and we distribute them across the drives in the system. We do that in our SAS-based systems, and we would do the same thing, or we do the same thing in our Ethernet-based systems. So the data protection is managed above the levels of the drives and the enclosure. Right? If we were to do within an enclosure RAID, for example, that would create undesirable fault domains and local domains. You know, if there was 100 drives that would be tied together in RAID groups. So at the scale of thousands of drives, we really believe we need to treat them as a single pool, and the protection is done across all those drives consistently rather than some kind of hierarchical RAID scheme.
Okay. Thank you. So, without further ado, just let me close off the presentation by thanking David Slick for his object drive overview, Enrico for talking about some products that he comes across commercially, and for Eric in giving us some background, some idea actually about the kind of experiments that storage vendors have been undertaking over the last few years in an attempt to bring these object drives to fruition. So, on your way out from this presentation, I would be immensely grateful if you rate the webcast. Remember, 1 is, I should have been off playing golf, or something like that. And 5 is, wonderful, let's do more of this. And we'd be really appreciative if you put some comments in there as you leave as well. The webcast and a copy of the slides are already up, and you can see the address there at SNIA.org, Forum CSI Knowledge Webcasts, and you'll see a copy of this presentation up there. And a Q&A for those questions that we couldn't get to, and there were a number of them, we'll answer within the week and post that on our website at www.sniacloud.com. You can also follow us on Twitter if you're into Twitter in a big way. But in the meanwhile, thank you very much indeed. Thank you for attending the presentation. Thank you to our speakers today. And have a good rest of your day while you contemplate the future of object drive technology. And remember, visit the SNIA website, get more information, and let us know on the ratings on the way out of the kind of information you'd like to see in the future. Thank you very much indeed, and goodbye.